what we're gonna do today is last class we did quadratic functions. So now we're gonna take it up a notch and do polynomial functions. Okay, it's all polynomials a whole week. A whole week. So today is polynomial function introduction. And then we're gonna go really deep into polynomials with more algebra stuff. And I believe on Wednesday, I'm gonna introduce to you guys a new theorem. Not a new theorem, a theorem. I don't think we've discussed what a theorem looks like in math in this class. So I'll kind of explain a little bit about it, but we'll have to wait until Wednesday. All right, so the warm-up. Today is the 6th, I think. Is that right?
Yeah.
All right, we're March. All right, don't forget your first name and last initial, please. And here's the warm-up. It says describe the differences between the following functions, and whatever you feel are differences, describe as many as you can. So I have f of x equals 5 to the x. We have g of x equals x to the 5th. We have h of x equals 1 over x to the 5th. Try to describe as many differences as equal this, so that when I'm taking the word, I see what it's in the votes. Any visual differences? Any differences like about the concepts, about functions? Domain stuff. You remember about some vocabulary about exponents and give you guys about 1 more minute. Okay, so just share with your classmates some of the differences that you were able to conclude, that you were able to find. Maybe they included some of yours, maybe they have different ones. Chicken.
Instead becomes bigger, it becomes bigger. And like where the is like one of the events, like events that which events that are yeah, I feel like that. It's odd number to the.
All right, guys, so let's see. Let's go by row. Someone in this row, just share one of the things you mentioned. Anybody in this row? Go. Logan, sorry. Logan. What's one thing that you mentioned?
Convex is a long one.
This guy here, okay,
That's compared to the rest of us.
okay. Let's see, so there's log forms, someone hiding here. Okay, right here, thank you. Someone want to share out one of the differences? Yeah. me.
X equals to X to the power -5. Because an exponent's in the bottom. So that
Gotcha.
means here.
So like if you rewrote it, you're saying you couldn't be writing with the negative exponent. Okay, good. All right, let's go to this row right here. Someone want to share out? This includes you guys in the back. If you guys are down for it.
I said that g of x is a polynomial. Well, I actually don't know if it's a polynomial or not.
Okay, so you're saying this is a polynomial. And then this one, you don't know if it is, right?
Yeah.
So I'll put polynomial with a question mark.
Yeah.
Okay. Beautiful. Now someone here in this row right there. Anything you wanted to include? Let's see. Someone pick a number between 1 and 5. Between 1 and 5. 4. All right, let me go 1, 2, 3, 4. Go for it, bud. Yeah, what's something that you mentioned?
The g of x, you can say that f of x is the trinomial.
Okay. This one right here, not g of x, right?
Yeah.
Okay, let's see. All right. All right, I'm getting all this vocabulary. I like it. Thank you. All right, someone here.
I said f of x and g of x are kind of the same, it's just they're flipped. So the
Okay,
5 and the x.
okay, so let's write this. So you're saying they're the 5 and x flipped. Is that 2 piece?
Yeah.
Yeah, flipped. Okay, cool. And then the last row. Yeah, go for it.
I just said that the first one has an exponent that is unknown, whereas the second one is a known exponent, but the variable is unknown.
So this one is x. So exponent is unknown. Here exponent is known. All right. What do you guys remember the vocab word for what the 5 is? It's not the exponent, the base. The base. So here exponent is unknown,
Base is 5.
but the base is known. Versus here, the exponent is known. And the base is unknown. So that kind of probably has to do a little bit with this right here. Right? Okay. Sweet. All right, let's see. So I see a lot of for these two. And then this one, maybe when we compare it this way, it kind of looks like this one, right?
Why is it the same except a fraction of one?
Okay, okay, yeah, so you're saying it's basically like this guy, but it's just like written as a fraction that's underneath. Good, good,
Inverse.
okay. So fractions. And so you're saying maybe it's the inverse of G. Okay,
Are G of X and F of X, or G of X and H of X, odd functions, but.
okay, so you're saying this is an odd function, or are you asking if it's not? Okay, odd function, and an odd function. Okay. And then this one you don't know, right? Okay. So before I bring down the projector. Okay, let's see all this stuff here. So you guys mentioned. One of them sounds like you should feel more confident that this polynomial. This one you're not sure. And then I heard the word trinomial, and then I heard the word log. Okay. So this will show up later on. We will see that when something is written in exponential form, you can rewrite it in log form.
Log base 5 to log X.
If you wrote this in log form, which we'll go over, correct? This would be log base 5.
And then there's X is right.
So if y equals 5 to the x, in log base form, it'll be log base 5 of y is equal to x. Don't worry about that. We're gonna do that towards the end of the semester. Okay? But that's kind of, there is a relationship, all right? For the word trinomial, that is what you guys have been doing with quadratics. So trinomials so far have been looking like this. So when you guys see the word trinomial, it means there are how many terms? 3 terms. 1, 2, 3. So in this case, how many, is there anything adding to this one? So that also has a special word. What if this one's called trinomial for 3? What do you guys think? One term? Monomial. Yeah. So when you're just dealing with one term, that's going to be a monomial. Okay. Let's see. Okay, and then I want you guys to look. Let's look at the graphs because I wasn't expecting you guys to know the graphs, but I do want to see. Let's look at what the graphs look like real quick. Okay. Let me go to Desmos real quick. All right, let's see. So we got f of x was 5 to the x. So that's what this one looks like. That one is an exponential function. Okay. Then there was g of x, which is x to the 5th. That one has like that curvy s. And then h of x was 1 over x to the 5th. And that one looks like 2 graphs, but it's really 1. Okay. So this guy here, if I go to home, whenever we're dealing with, not whenever, but most of the time when we're dealing with fractions where x is part of the denominator, these are going to be called, this is what we're going to deal with here, 4.7, called the rational function. Okay, so we're going to be doing that next week. The other one, the f, that one is called an exponential function because like you guys identified here, the unknown is the exponent. We're going to do that here, almost like 2 weeks before the semester's over. And so the one we're going to deal with now is the middle one. Okay. The graphs are going to look like these little S shapes like that. Correct. Yeah. So one property we're going to see is that if the power is even, it looks parabola-ish. Okay. Okay. It gets boxed here. That's a property of that. So if it's odd, like 1, that's a line, just x. 3, S curve. 5, 7, 9, 11, 999. It's like bam, bam. Correct. It's like exactly, they're opposite sides, exactly. Yeah.
I was saying, is it because if the base was like, let's say -2, it was even powered. It would
Correct.
be-
It forces it to be positive, correct. So when you plug in negative x values, because they're being raised to an even power, they're all gonna become positives and the negatives cancel. But when the power is a negative and I plug in a negative x, it'll stay negative. So then the y values are negative as well. Exactly. But then there is the coefficients in front of it. If that's negative, then that does affect the sign. So that's all the stuff we're gonna figure out today. So it flips, exactly. So it's just a reflection. Okay, so that's why today is a little bit of like, it's kind of tying in a lot of the stuff we've been doing. And I broke it up into a lot of some diagrams to kind of help you guys put the pieces together. Okay, so that's what we're gonna play with today. And we're gonna introduce a little bit of calculus notation. Woo! And we're gonna talk about some infinity stuff. All right. All right, guys, pass up your warm-ups. Pass up your warm-ups. Good job. Let me stop sharing my screen. Oh, I was never sharing. You guys will be here. Thank you. Okay. We're gonna do a lot of factoring today, okay? So make sure you guys ask those great questions that you did last week. All right, section 4.6 on polynomial functions. All right. So we're gonna define kind of what a polynomial is gonna look like. So we're gonna say a polynomial function is a function of the form. This part's gonna look a little scary, okay? It's gonna be a general form of all these polynomials. Let's see. Let's leave this empty for now. Leave this empty for now, and then I'm gonna have you guys figure out what it's gonna look like together. Let's look at an example real quick. Leave this empty. Let's look at polynomials that you guys have already seen so far. So quadratics, the ones we did last class. That. And let's do another one that's a linear function, in slope form. Let's say something like this. Okay, how many terms are in this function f? There's 3 terms, okay? How many terms are in this one? There are 2 terms. So what's the highest power of x for g? 1. What's the highest power of x for f? 2. So for polynomials, it's whatever. 100 power to the 100, power to the 44th. It's whatever power we want it to be. So normally we say this is the, before I get there, so let's see. So we're gonna generalize a polynomial to what's called the nth power. The nth, okay? So x is gonna be to the power of n, okay? Now, that's like this guy here, but do you guys see there's a coefficient in front? Okay, we're gonna name that coefficient a. But we're gonna say it's the coefficient multiplying x to the power of n and put a little subscript to say it's the nth coefficient. A to the nth coefficient. Let me actually go more like this. So it's a subscript. Because we've been doing A, B, C for quadratics, but the alphabet has 26 letters. Okay, and I can have a polynomial with 50 terms. I run out of letters at some point. So instead of using different letters, we're going to stick to the letter A, but just enumerate it with a subscript. Okay, so if this power of x is n, and I bring down that power by 1, what do you guys think that next power will look like? It's going to be n minus 1, because it's 1 less than this. So what will this coefficient look like? Exactly like that. Okay. And you just keep doing that. So in math, the way you write and you just keep doing that is, I'm going to say plus, and then you put dot, dot, dot. Like that pattern will then continue. Until, let's say, maybe I get to the x to the third power. What will that coefficient look like?
It's subscript of 3.
3, yeah. A3. And then x to the second power. A2. And then A1 for x to what power? 1. But you just leave it as x. You don't have to write the 1 here. Because x to the 1 is x. Do you guys see how every single term has an x though? Was that true for G and F? Does every single term have an x? No. No, right? Here, this one doesn't have an x, and here, this one doesn't have an x. So that one, the way the definition is going to be written is a to the 0, because there's no x. You can think of it as x to the 0. But a non-zero number raised to the 0th power is just going to be 1. So it's normally written like that step. Okay. But this enumeration of the subscripts gives you the name of which term. So this is called the first term of x. This is technically, I guess I don't want to call it the 0th term, but it's the 0th term. First term, second term, third term, and so on. Okay. So part of what I wanted you, what we're going to do in the beginning is just get familiar with the notation. Okay. So here, how did I write it here? Yeah. So here, this 4 is the coefficient of x squared. So it's going to be, actually, let me do it like this. What's A2, what's A1, and what's A0? So when it says what's A2, that's asking you what's the coefficient of x squared? That's how you want to read that. What's the coefficient of x squared? The number in front of x squared, which is 4. So this is 4. What's the coefficient of x? 5. And then normally this guy here is called a constant term because it has no x's on it. So this is usually referred to as the constant term, the one without an x. So here the constant term A0 is -2. Here, how many terms are there? 2. So it'd be A1 and A0. So in this case, A1 is
5,
5 and
1.
1. Here's a trick question. What's A2?
I mean, it doesn't exist because it's 1.
Well, if it was 1, then there would be something that looks like this.
Why do I want to say 0? Because it's not gonna make the 5 0, is it?
Nope, it's 0. So it's not there. Yeah, normally they won't ask you that, but yeah, okay. So this is a trick question, right? All right. So these are the coefficients of the polynomial. So there's gonna be a lot of vocab, I guess, so I apologize for all the definitions. Today's gonna feel like you're in a foreign language class.
Oh, wonderful.
I know. Okay, some more vocab. Some more vocab, that's important. So we're gonna say the degree of the polynomial. The degree of the polynomial is gonna end up equaling the largest exponent of x. Or I'll just put the largest x. So the example that we have here, 4x squared plus 5x minus 2 is of degree, what's the degree of this polynomial?
2.
The highest exponent, which is 2, is of degree 2. What's the degree of g?
1.
1. Good. All right. We're gonna say the leading term, a n x to the n, this guy right here, smack in the front. The leading term is going to be the term with the highest exponent. All right, so let's use an example. The leading term of 4x squared plus 5x minus 2 is,
5.
what's the leading term?
Oh,
The whole thing. So you start by looking at which one has the highest power of x, this one, and then you include x with its coefficient. So it's all of this. That's the leading term. That's going to be useful today. Okay? That leading term has a lot of power. All right, I got one more, sorry. All right, the leading coefficient, is going to be the coefficient of the leading term. So in this case, the leading coefficient of 4x squared plus 5x minus 2 is. What's the leading coefficient? Just the number 4, just the number 4. Your eyes want to, here for this one, your eyes wanted to go here, here, your eyes want to focus on this guy. And for this one, your eyes wanted to focus on the degree. All right, a baby practice one, a baby practice. Find the degree, leading term, and leading coefficient of, let's call this polynomial negative 7x to the third plus 5x to the 40th minus 3x to the third plus 9. Practice that vocabulary there. You see it on the video. Yeah, you can. And so just put, as you're filling it out, just what's the degree, what's the leading term, and what's the leading coefficient. Yes, sorry. That's a little squish. So it's negative 7x cubed plus 5x to the 40th minus 3x cubed plus 9. Oh, wait, hold on. Nah, fuck it, I'll leave it. Folks in the back, can you guys see this number, the exponent? What is it? 40. Good. 40. Give you guys an idea. All right, what's the degree?
40.
Highest exponent, which is in this case 40. What's the leading term?
5x to the power.
You look at the term with the highest exponent, which is this bad boy. So it's 5x to the 40th. And what's the leading coefficient?
5.
That 5 right there. What's going to happen on the homework when you guys are like multiplying and doing all this stuff is your polynomials won't be in what's called descending order.
Yeah.
I purposely did not put it in descending order. What does that mean? That means that when you read it from left to right, the exponents won't be decreasing. It'll just kind of be all over the place. So it's very helpful for you when you're doing your algebra to rewrite it in descending order and combine any like terms. Okay, so this guy here, if I wrote it better, it would be written as, I start with my leading term, which is 5x to the 40th. And then these actually combine. Negative 10x to the third cubed, and then plus 9. Doesn't that just feel better? I don't know. It just feels better. It's like, it's like organized. Okay. So that's a lot about the way the function looks like. Okay. That's what we're going to be dealing with, all this stuff today. So what I want you guys to do is I'm gonna give you a handout. There's only two sides of it, the front, the back. We're gonna talk about it in a little bit later on. But what I want you guys to do is go on your either graphing calculator or Desmos. And I just want you guys to graph these polynomials so that you can practice knowing how to put that on your calculator. And then reflect on the questions below. Okay, so please take out any graphing devices. If you have your phone, go to Desmos. While I pass these out. And guys, when you graph these, just kind of do a sketch. Okay, just do a sketch of the graphs, get a feel for them. 1, 2, 3, 4, 5. One, 2, 3, 4, 5, 6, 7. If you need help knowing how to do this on a graphing device that you're using, let me know, okay? I'll go around and help you out. Sorry.
Kind of.
Is it okay with you said? Now try again. Awesome. We don't need help. Yeah. Yeah, first
No,
you
go back.
write it and then you write
No, but that was the problem. She has the same
Same thing?
issue. Yeah, the blue ones must have come.
it. So what we did is we just reset it back to default. Let me see if you use this X-ray. Oh, you see that equal sign? It has to be, like, folded so that it reads like you want to let that hold. Yeah, 'cause sometimes you end up with like so many equations, you can like select which ones you want graph. And which ones you do not. Alright, good. Back in the 90s and forties, probably when I had to go to computer lab. Maybe like early 2000s. Yeah. That's not so long. Let me know if you need help. You guys do that? Let me do this here. Super fast. Okay, let's see what you guys have. We got y equals x cubed. It's 5x squared. It's x. Then you have x to the 5th power minus 1x cubed. And then we got x cubed. The 6th power. Minus 1x cubed. Ah, so many. Hey. Let's settle down for what we're doing is we're doing polynomial functions. So right now, folks are just grabbing a device and sketching a graph of this. Kind of get a feel for what they look like. If you finish graphing them, just kind of look at the questions below and see what you know, try to think about those answers there. Oops, that's just. Some point, just check with your classmates, see if your picture looks the same. Maybe you made a little baby mistake. Just be careful. Just see if you guys have the general shape.
Yeah. Like,
This one.
You guys are doing a great job. I think you're labeling special points. Nice.
was hers right?
It's related to the first question below.
Because that's what I meant to draw. I just can't draw. So you're saying
Oh, okay,
that's
okay.
what's- like, that's what I saw too.
Okay, it's okay. A little bit of the art skills coming out
Great, yeah.
during this section. All right, let's see. So our first graph looks like a W. Okay. When you guys were graphing this, this W shape here, did you have to lift your pencil at all as you were doing that? Would I have to lift my pencil if I draw this?
No.
I do not. No, it's just a nice little curve. Woo! Never have to lift my pencil. Would this be a fun roller coaster?
Yeah.
Depends on the thrill, right? Okay. All right, let's take a look at the second one. Let's answer some of the questions. So does this graph have any sharp corners? No, no sharp corners. Right, it's nice, smooth little turns here. Any holes on the graph? There are no holes on this graph. All right. Important. These last two are very important. What happens to the graph as x is supposed to say becomes more and more positive? So as x gets more and more positive this way, what happens to the graph itself? How would you describe that to a high school student? Oh, I have high school students. Let's say to a fifth grader. Like really plain words. Yes. It's growing, but it won't grow exponentially. There's going to be a difference between growing exponentially and something different. Yeah. Exponentially, I'll just give you the like quick little definition, is whenever something is going to increase by the same percentage over and over and over. That actually won't happen with polynomials. And it tends to be some J-shaped curve, but that's like the most basic one. And then there's complicated ones where you can have like a piecewise. Remember we talked about piecewise? Or at some point you can have it be exponential, but yeah, there is usually that J shape. Yeah. But in this case, all of these will not be growing exponentially. Yeah. Question mark. Symmetry between, like when you cut it in half, is that what you're referring to? Okay. So as you keep going, that symmetry seems to stay. All right, cool, good. Now it's not exact symmetry, because notice this guy dips a little more than this one. So it's not almost symmetric. Yeah, it's almost symmetric. Okay. Now the third question, what happens to x? What happens to the graph as x becomes more and more negative? It's still growing as x becomes more and more negative. Okay. So what I want you guys to realize is when x becomes more positive, you're reading the graph from left to right. That's how you're going to look at the graph. But when x is getting more and more negative, you're reading the graph from right to left. Okay? Questions? Yeah.
If ever asked that, you have to start out like, oh, initially it's negative. It begins negative and corrects itself to positive, or can you just like say the long term of it?
The long term of it.
Okay.
Yeah. So this question that what happens as x becomes more and more positive, essentially you want to ignore what happens in the origin area. Like you just care about like x being just more and more positive. What seems to happen to the graph? It's going up. Yeah. So we'll talk about that. Yeah. So I'm getting there. Good question. Okay, let's go to the next graph. Any sharp turns here? If I zoom out, it might look like it, but when you zoom in, it still turns nice smooth little turn here, right? It's still roller coaster-ish. Okay. Sharp is like kind of like the absolute value. Right? When we looked at this guy, or let's say I flipped it. Let's say I added here, hold on, let me move it. Okay. See, you don't want that roller coaster. Right? That's like a crazy sharp, crazy turn. Okay. Polynomial, on the other hand, still has a bit of a twist to it when you're turning, okay? And so that's why I'm asking that question. We're gonna notice that polynomials never will have sharp, spiky turns like that. They're always nice and smooth, okay? Are there any holes here? There won't be any holes because it turns out when I think about the domain, I don't have any restrictions. I don't have fractions, so I don't have to worry about dividing by 0, and I don't have square roots, so I don't have to deal with negatives. So in this case, polynomials, are there any restrictions to our input values? No. So how would I say that mathematically that there are no restrictions in my domain? What's the interval of my domain? Negative infinity to infinity. So polynomials, that's another nice property, is that their domain is everything, all real numbers, from negative infinity to infinity. What happens as x becomes more and more positive? The graph is growing. What happens as x becomes more and more negative? Let's not say the word shrinks, because that has to do with like, we can say the word decreases. What happens to, look at the y values, guys. What's happening to the y values? They're getting more, they're getting lower, they're getting more negative. So they are decreasing. Okay. All right, nice. Let's look at the next one. Again, nice smooth turns. What happens as x becomes more and more positive? What are the y values doing? They're going down, so they're decreasing. So the graph is, we're going to say, decreasing. What happens as the x gets more and more negative? What's happening to the y values? The y values are increasing. So we're going to say the graph is increasing. In this case, when x becomes more negative. All right, last one. All right, again, smooth turns. This would be a pretty dope roller coaster. You know, you go, and then comes the drop. What happens as x becomes more and more positive? The y values are decreasing. What happens as x becomes more and more negative? Also decreasing. All right. I'm going to call the polynomials, as you're getting farther away from the origin, I'm going to call those the tails of the polynomial. Okay? The textbook doesn't call them that. We're just going to call them the tails. All right. Good. All right, put this back up. Good job. All right, so let's talk about these tails. Show this. No, okay. So to describe the tails of a polynomial graph, we study the graph's what's called end behavior. End behavior. What's happening at the ends of the graph? Okay. And there are 4 new types of notation that I'm going to show you guys to describe the tails or describe its end behavior. So one of them is the second question where I said, what happens as x becomes more and more positive? To write that mathematically, we're going to say x is approaching infinity. Okay. when you guys see this notation, it means, the way you read it is x approaches infinity. Means x, x keeps getting more and more positive. That's what we're reading from left to right. Okay. The next one is going to be x approaching negative. So you would read that as x approaches, let's just say negative infinity. Just save some time. Doesn't mean equals though, okay? It means it's approaching. So your head should think of like it just continuously keeps going in that direction. Means x keeps getting more and more what? Negative. It's a lot of writing, I apologize, but I'm translating the symbols to you. That's what's happening. Okay. Okay, now instead of saying the y values are approaching something, we're going to say f of x, which are the output values, are approaching infinity. That's different. This is not talking about x. It's talking about the output values, which most of the time we're thinking of the y values. So this you read as f of x approaches positive infinity. Means the output y values, in this case is y values, keep increasing. Just keep getting higher and higher and higher. They keep increasing. And then the last one is f of x approaching negative infinity. You read that as f of x approaches negative infinity. And it's going to be the opposite. Means the output y values keep decreasing the way you guys were telling me the y values were. They kept going down and down and down. They're decreasing. All right, I'm going to give you some time. That was a lot of writing. I apologize. Okay, so watch. Let me show you how we're going to use this. And then I'm going to have you guys do it on the graphs that you just did. So it would say something like, this. It would say describe the polynomials and behavior. And let's say the graph looks something like this. And so the way you do it is you first start by telling the reader the direction you want them to read the graph. Do you want them to read it from left to right, or do you want them to read it from right to left? So we're gonna start with these two first. Okay? So the way you would write it is like this. You're gonna say as, or hold on. If I do that. Remember I was telling you about the tails? Okay, let's say I want to describe the right tail. Which direction is x approaching? Positive infinity. So if I want to describe the right tail, in math, I have to write as x approaches positive infinity, what are the y values doing? What are they approaching? As x goes this way, what are the y values doing? They're going down. So f of x is approaching negative infinity. Negative. That's right here. This is the right tail. That's you in math telling the reader what the right tail is doing. If I want to describe the left tail, what is x approaching? Negative infinity. As x approaches negative infinity, the y values or f of x is approaching. The y values are going up. So then I put positive. That's the left tail. So this is a sentence, a math sentence. Okay? And the way you read it is, as x approaches positive infinity, the output values are approaching negative infinity. Or as x keeps getting bigger, the y values are decreasing. So on all the graphs that you guys just did, I want you guys to describe the right tail and the left tail of each graph using this notation. Okay? So you could do it here on the sides. Use this new notation to describe the tails of these four graphs. Let me just check with your classmates. I'll help you out as well. Oh, I have a meeting at 3:30 though. Okay, so I'm gonna have to leave. I can spend like maybe 5 to 10 minutes.
I just need clarification.
Okay. You guys are ready? Calculus notation. This is calculus notation. Notation, yeah, it's a very common, very useful notation. Or maybe it's just math notation, preparing you for calculus. Correct, yeah. Yeah.
So wait. This would be as x is positive.
Not quite. We will in a little bit, actually. Right now, I just want you to look at the graph.
Oh.
Yeah, just by looking at the graph. Class, also, I know I'm a little anal about this, but make sure you put arrowheads. Because that literally means this behavior. If you stop it here, mathematically, it means the graph stops right there. And that's not true. It actually keeps going. It's better if I just leave this thing like this. Yeah, there we go. I had to do that. You guys? Okay, so you're gonna use that for your notes on the homework. The way you're labeling the end behavior of your graph. Okay, so I want to focus on one of those graphs. I think it's the third one. Let's look at that third graph. Is that the third one right here?
Yeah.
Yeah, okay. So let's look at the right tail as x goes to positive infinity. Now, as x goes to positive infinity, you guys want to like get crazy with like what that means. That means it's not going to 100, it's going to like 1,000, 1 billion. Like it's getting really, really big. Okay. Okay. Let's go back to the polynomial now and let's look at what it looks like. So notice that if I plug in the number 10, that number 10 gets plugged in here and it gets plugged in here, right? So when I plug it into the first or this leading term here, what kind of number will you get if you plug in 10 there? It's going to be 10 cubed, which is huge. And then the negative negates it. So it's a really big negative. And when I plug it in here, I'm going to get 10 squared, which is 100, times 3 is 300. Okay. But the overall output is going to be negative 700. Why did that happen? Why did we get a negative answer?
Because the first is a negative.
The first is a negative, and it's way bigger than the second term. What if I just keep adding more net positives? Like, let's just say I do like a 5,000, maybe not 5,000. Fuck it, 5,000. Let's do a term with degree 1, and maybe I add 10,000. Okay. See, right now that negative it got overpowered, so it actually became more positive. But let's let x go to positive infinity. Boop.
So if it's only in the first like
The first term,
term, and then how big x will be.
how big you're plugging in the values. Yeah. So the moral of the story is, as x gets really, really big, what ends up overpowering the signs of the outputs are what? The largest exponent, which is the leading term. Okay. So if you guys look at the back of your sheet, it turns out that you can know the polynomials and behavior without looking at the graph by just focusing on the leading term. So let me write that part out. Because that leading term has the highest exponents, which controls how the y values are going to be increasing or decreasing. Okay. So I have a little table there that I provided for you guys. So let's say your polynomial has looks like this, but this is the leading term. Okay, that's the leading term. So the way you use this table, it's saying this column here, you have even degree, even degree, even degree. Remember how in the beginning we were noticing that if the degree was even, the tail was going up, right? And then when it was odd degree, it was like opposite. Okay. So we're going to break it down that way. You're going to see if it has even degree or odd degree. Okay. And then what affects it, as you guys were noticing, is the coefficient being positive or negative, because then that does that reflection piece. Remember, we're looking at that as well. So if the leading coefficient, A of n, is positive, and your polynomial has even degree, it turns out that the end behavior of the right tail is as x goes to infinity, f of x goes to infinity, and same with the left tail. As x goes to negative infinity, the left tail goes up. Okay. If it's even degree, but now the leading coefficient is negative, then you plug in really big x values, but because you have an even degree, they're going to be positive, and this coefficient will force them both to go down, both tails to go down. And you guys, as I'm writing this, you guys can look on what you guys did from the front. Notice that number one, what degree is number one? It's even degree, it's degree 4, and the leading coefficient is positive or negative? It's 3, so it's positive. And what do the tails look like? Both going up. What other problem has even degree? Number 4 has even degree, and the leading coefficient is negative. Both of the tails went down. Okay. If it's odd degree and the leading coefficient is positive, what happens to the right tail? It's going up. And as x goes towards negative infinity, the left tail goes down. Okay. We don't know what happens in between. We just are discussing the tails right now. If the leading coefficient is negative and you have degree odd, what happens to the right tail?
Like, it's left and, yeah,
Going down
and
and
going the opposite.
going the opposite, correct. So they always go opposite. This one is which number on the sheet here?
The third one?
Odd degree with a
With a
positive
three.
number 2. Notice it has degree 5, odd. Leading coefficient is 1, which is positive. And notice that the tails match,
Yeah.
the end behavior matches. And then number 3,
Would be the
degree is odd, coefficient is -1, and it matches this end behavior. So on the homework, when you look at a polynomial, it turns out you can know its end behavior strictly by just focusing on the leading term, because that's the one that eventually will overpower the sign of the y values as x is really big. Okay. All right, you've earned a break. Let's take a break. Come back at 2:14. And put your factoring hats on. Sorry. Here, I'll say 2:15. Yeah. Let me pause real quick. Hold on. I'm screwed with the recording. Okay. All right, guys. So this table here, I'm going to leave it so you can reference it. This is to help you find the polynomials and behavior. We're going to return to it later, okay? What we're going to do now is we're going to focus on what's called the polynomial local behavior. Which is all about like finding the intercepts and the shape of the graph in the middle part of the graph. So we now focus on studying a polynomial's y-intercept. So y-intercept, x-intercept, and the shape of its graph, the shape of its graph. Those are the 3 things we're going to focus on. So when you guys hear that local behavior term, it's talking about these things here. Let me see, I gotta make sure I leave a lot of room for this stuff. All right, I think that's fine. Okay. So let's start with a polynomial that you're familiar with, which is a quadratic. So consider a degree 2 polynomial in factored form. I'm using some of the vocab that we learned last class. So let's look at this guy here. F of x equals I'm gonna first write it not in factored form, and then we'll turn it to factored form. Okay. So I think we're calling that the standard form. So let's say I wanted to factor this guy as much as I can. Okay. Notice the coefficients are all even. So we can take out let's take out a 2, but let's take out that -2. So that our leading term doesn't have a leading a negative coefficient factor. If I take out a -2, let's see, you're going to be left with
X squared minus
minus
root of x minus 8.
8. Okay, and now let's factor that trinomial. Right, that word that we learned has 3 terms. Let's factor this guy out. Give you guys some time to think about it. I need you guys to practice factoring. So what 2 numbers are going to multiply to -8? And then when you combine like terms, it'll add to -2. Yeah.
X minus 4, X.
X minus 4, X plus 2. Good. So this is the polynomial or the quadratic. This is in factored form. Okay. Okay, let's see. Let me go in black. So what are the x-intercepts? Set this equal to 0. Good. So then what will make this 0? 4. And what makes this 0? -2. So then the intercepts are 0, -0. Good. Sorry for folks in the back. I'll try to write big. How would I find the y-intercept?
Did you plug those, plug one of those into the original?
No, not quite. Not quite. What's the x value of the y-intercept?
0.
0. So you could plug in 0 here, or you can plug in 0 here, and it's going to be 16. Remember, each form gave you different pieces of information. Here, this tells you the y-intercept. If I plug in 0, I get 16. So then the y-intercept is 0, 16. So then that means that the shape of this graph, oh, careful. The shape of this graph is going to cross the y-axis at 16. It's going to cross the x-axis at 4. And it's going to cross at -2, the x-axis as well. So it has to cross here, it has to cross here, and it has to cross here. So how would it be shaped? What do you guys think? It's a quadratic, so we know it has to be a parabola. Is it smiling facing up or is it frowning facing down? Facing down, leading coefficient is negative, has to be facing down. And so it goes up and down. We can find the vertex as well, but right now we're not going to do that. Okay. Yeah, more vocab for you guys. Okay, you probably heard it, but if you haven't, it's more vocab. Okay. What are we calling these 2 points? The x-intercepts. The x values of those x-intercepts have special names. Okay. So these x values. So the x values, x equaling -2 and x equaling 4.
Axis of symmetry.
No, not quite, not quite. Are called the zeros of f. Because when I plug in that x value into the function, I plug in that x value into the function, what has to be the y value? Has to be 0. So when you plug them in, they give you 0. That's why they're called the zeros. Okay. Some textbooks have another name for them. They call them the roots. So zeros or roots are the names of these x values. I'm thinking roots has to do with like, because it hits the x-axis, so it's like it's rooted there. What I'm thinking, I'll figure that one out. Okay. So the homework has been telling you for the quadratic part, it has been telling you find the x-intercepts. Now the question, I can have you do similar algebra, but instead I'll say find the zeros. That means you just need to give me the x values, not the actual points. Okay. Cool. Okay, another example. More factoring. All right, now I'm going to word it that way. I'm going to say find the zeros of f of x equals x to the 5th minus 14 x to the 4th plus 49 x cubed. So we're trying to see which x values you plug in so that the function will equal 0. So what's our first step? What's our first algebraic step I need to do here?
Don't you need to find the x? Like factor it
I
out?
basically have to do the x-intercepts,
Yeah.
but what's the very first thing I need to write?
Turn it into 0.
You got to set the equation, the function equal to 0.
Yeah,
That's the very first step. I need to set the equation equal to 0 so that I can start solving.
yeah. Is it because like if it's in f of x, it's still it's a function, but it's not like a function to serve yet. So when you switch that into 0, you can solve the equation.
Yeah. So this what I wrote here is essentially saying this.
Oh, okay.
When will the function equal 0 or which x
Okay.
values? So then what is that function? It's this one right here.
Oh, okay.
Yeah, that's kind of what's being written there. All right, here we go. I got to solve for x. It's not a quadratic. But do you guys see how each term does have an x?
Mhm.
So there's a different type of factoring called the greatest common factor. So my teacher used to call it take out the junk. Okay, what does that mean? All of these can be divided by x to what power? To the 3rd power. So I'm gonna factor out x, the lowest power of x possible. Okay. No, I'm gonna factor out the highest power of x possible. the highest power of x. But this guy, the highest power of x that I could take out from here is the x cubed.
Mhm.
So I'm gonna factor out the x cubed. I'm removing it for each of these terms. So if I factor out an x cubed from x to the fifth, I'm left with how many x's? I'm left with 2. Here I'm left with, yeah, minus, how many x's did I remove?
Three.
3. So I'm left with 1. And here I removed all of them. So I'm just left with a 49. So that's kind of what we did. We took out an x cubed. Okay, I'm left with a quadratic. So that quadratic, I have to factor it now. Okay, so let's see. So this quadratic, this trinomial here, a polynomial with 3 terms here. It's kind of like what we did from here to here. Okay. When your quadratic has a 1 here, the factoring is easier because it turns out that it's going to be x and x,
Mhm.
and then you got to think of 2 numbers that multiply to your constant term, but add to a negative 14.
7.
7,
-7.
negative 7, and negative 7. Beautiful. Good. Okay, good.
Did it change anything? We have the same number twice, like 3x notes.
Algebraically, no. Graphically, yes. Yeah, and I'm gonna talk about that. Yep. So we're going. Okay, I'm not done though.
Mhm.
So now I gotta see, and then my goal is what's the x values that will make my function equal to 0, right? So what makes this equal to 0?
7.
7. What makes this equal to 0? 7. What makes this one equal to 0? Let's double check real quick. So I'm gonna set it equal to 0.
Mhm.
have a question.
Yes, question.
feel like I already know the answer to that. Why for that one, for -2, we didn't have to have one, it's because we don't have an exponent.
It's because it doesn't have an x.
Yeah.
Yeah.
Yeah,
This has no x versus this one does, it is an x.
so,
Good observation.
okay.
Yeah, so if it's just a numerical value, there's nothing to plug in, like I
It's
can't,
just A alone.
if it's just a alone. It doesn't produce any other any other zeros. Because there is no x,
But the A in this case is 1, but X still.
but there's still an x, correct? Yeah. So if you were unsure, what can I plug in here to make it 0? You just set it equal to 0. Remove the cube by doing what?
Square root.
Cube rooting.
Yeah.
Cube rooting. The cube root and the cube cancel. What number multiplies itself 3 times to give you 0? 0. So what are the zeros of the equation?
0 and 7.
Only 0 and 7. Only 0 and 7. Correct.
And then, but because there's 3 of them, I remember like, whatever the leading degree is, it would reflect on how many roots there are. Because, here,
Yeah,
I know you put 3 lines under the 0 because there's an X cubed. Actually,
correct.
you could do that for 7 because there's 2 sevens, and you're saying.
Correct.
2 lines under that.
Yeah. So one property of polynomials, we'll get there later, is that what's the degree of this polynomial? 5. If I factored it, can it factor into 6 different things?
No.
No, because then if you multiply them all out, what would be the degree of x? 6. So it turns out that if the degree is 5, it can factor into at most 5 different things. So it'll have at most 5 zeros. But in this case, some of the zeros repeated. Okay, but this guy part of it is that there will be at most 5 zeros. Okay, that's an observation. Yeah.
How is 49 your y-intercept when you have your x value of 0, 0? So would that mean that would be 2 times it goes through the y?
Well, it won't be the 49 won't beat the y-intercept because notice it's not a quadratic. Also notice that if I plug in 0, everything is 0.
Oh, okay.
Yeah, versus here, this didn't have an X with it.
Well, not only that, but on these graphs, they have as well as a point, but this one I don't.
Correct, yeah. So sometimes your y-intercept is 0, 0. Yeah, question.
Yeah, this might be kind of a stupid question,
go for
but like, you could plug in other values in the x's and still make it equal to 0, but how come those aren't the x and x?
What are the other ones you're thinking of?
For example, if we did 11.5 minus 7, 11.5 minus 7, and 3 cubed, would equal 0.
Well, whatever you plug in for X has to be plugged into all the X's. So I can't plug in some values here that are different from this one.
But you don't plug in 7 in the x cubed.
You do. You do. Like if I plugged in the 7, if I plugged in the 7 here, right? If I plugged in the 7, it would look like this. This won't be 0, that's true, but these are, so the whole thing will be 0. Because this will be, oh God, what's 7 cubed? Whatever that is. Yeah,
Mhm.
whatever that is,
Times 0.
times 0, anything times 0 is 0.
Mhm.
343, okay, so 343 times 0 times 0, yeah. So how many zeros are there? There's 1, 2, but this is just a repeated one. So now connect it graphically. How many times will this graph cross the x-axis?
3.
Where will it cross the x-axis? At 0 and 7 only. Okay, so here's where the algebra is talking to the graphical part of this stuff. Man, I'm probably gonna regret this part, but let's do it. Let's see what I'm saying. All right, another little bit of vocab. I'm sorry. Okay. How many times is this 0 a 0? Twice. There's a word for that. Okay. So we're gonna say this 0 has multiplicity 2 because it's a 0 2 times.
And there's like multiplicity for.
Exactly. Notice that see this equation we have right here? I can rewrite it like this. That. Okay. Whew, sorry. Okay. It's loaded today. See how the x cubed, you guys see the x cubed? Technically, if I expanded all this, it would look like this. X times x times x times x minus 7 times x minus 7. You see that? So here, 7 is a 0, 1, 2 times. How many times is this 0 a 0? 1, 2, 3 times. Okay. So this is gonna have multiplicity. This 0 has multiplicity 3 because it's a 0.
Well, in the multiplicities of ours, you have to add up to the 100.
Perfect. And then you'll notice that the multiplicity of all the zeros has to add to the degree of the polynomial. Okay. Maybe, so you maybe write that. I'm running out of room, but that's an observation. The multiplicities of all of the zeros will end up adding to the degree of the polynomial. I'm getting low key like giddy. This is so fun, cool. Okay. All right, let's pick break apart another example, and then I'm gonna give you guys 2, okay, to play with. What's the multiplicity of this zero? One, the multiplicity of this zero. What's one plus one? The degree of the polynomial. Good job. Okay, let's do another one that has different types of factoring. I'm giving you guys the whole shebang. The whole thing. Okay. One more done for me, and then I'm gonna have you guys try another one. Try some yourself. Woo. Stretch a little bit. All right, similar thing. Find the zeros of f of x equaling 3x to the third power plus 3x minus 2x squared plus 2. Minus 2. All right, guys, so we're looking for the zero. So what do we have to set? What do you have to do to start?
Put it in ascending or ascending order,
Sure. Let's say you want to put it in this ascending order.
so 3x cubed, minus 2x squared, plus 3x minus 2.
Okay.
And set that to 0.
So it's a zero, sure, okay, that works. All right, let's see, so like this one, these all had an x cubed in common. Is there a term, or is there a number or an expression that these all have in common? Something that they all have in common.
-1.
Yeah, but the leading term is already positive, so we're good with that. The only thing they have in common is the one.
But you can split them into two different things, can you?
So what we're gonna do is a different method called factor by grouping. Okay? Yeah. Where what you do is when you have 4 terms, you pair them up. And then you look at each pair individually and then say, what can I factor from each pair?
From the first pair, you do x squared.
X squared. So I take out an x squared. This guy here. And then you're gonna be left with
3x minus 2.
you're left with 3x minus 2. Now you look at the other pair. Do they have anything in common? One, only a positive one. So we'll just write that positive one that they have in common. And then when I take out a 1, what's left with it? The same thing. And how do you know you're doing grouping correctly?
Like this.
If these are look exactly the same, good. So then once you factor these out,
0 equals 3x squared minus 2x squared.
so what's happening is like now you're kind of factoring out this common term and you're factoring it out. And when you factor it out, you're gonna be left with plus 1. Like that. Okay. So these, think of it like now these are 2 different terms where they each have a 3x minus 2 in common. So you factor it out and then you're left with the x squared plus 1. Notice that if I multiply this whole thing with the 1, that's what this is. If I multiply this whole thing with the x squared, that's what this is. But now it let me factor it. Okay,
Now set both equations to 0 separately.
yeah, so now that it's factored, you can set each equation equal to 0. They're a little more complicated than these ones, right? So let's set them each equal to 0. Let's do this one first. Add the 2 to both sides. Divide by 3. Get 2/3. Here, what do we do? Subtract the 1. The thingy. Square root. What did I tell you guys? Whenever you apply the square root, you must always consider
Plus or minus.
plus or minus. What's the square root of -1 though? Oh, shit. We no longer have real numbers. Now we have an imaginary. Okay, there it is.
It's just I.
You can think of it as one eye. One eye, yeah. And you can write it like that, that's fine. Like this? That's fine, too. It's just 1 times I.
You have to put plus or minus.
You do, because you're applying the square root. So you get a positive answer and a negative answer. Okay. That's what you guys were doing when you're solving. Now graphically, where does a graph cross the x-axis? At 2/3. Does the x-axis contain imaginary numbers?
No.
No. So even though this is a imaginary roots or an imaginary 0, it doesn't actually do anything with the graph in this class. It has to do with other stuff here. In this class, it's only says that the graph will only cross the x-axis at 2/3.
But the multiplicity of that is 3, right?
Well, in this case, this is only a 0 once. For this guy. If there was another one like this, or if it looked like this, then it would have multiplicity 2 or 3 or whatever. But there's only one factor that produced that 0.
So there's no multiplicity,
Multiplicity 1.
but
Yeah.
the degree is 3. But the plus or minus
Plus or
5 is 2. Oh.
Stupid thing, yeah. Imaginary, that's right. Okay.
So you can combine them that way because it's basically the same as when they're next to each other and you distribute.
Oh, you're talking about from here to here?
Yeah.
Correct. Yeah, exactly. It's like you're undoing this funky distribution, correct? Yeah. Yeah. So in this case, I think on WebAssign, it says real roots. You're gonna answer the real roots. What does that mean? That your roots, your zeros are real numbers. So this would be what you would put on WebAssign. This technically is a 0, it's just an imaginary number. Okay? If I do all my work and all my zeros are imaginary, then you're gonna say no real roots or no real zeros. Or whatever WebAssign tells you. Okay? All right, guys, let me give you 2 problems. You guys can play a little bit. We might not finish the whole class, so we'll carry over next one to the next one. That's fine. All right, guys, so find let me just check something real quick. Find the zeros of that. So f of x equals negative x to the 6th minus 16x to the 4th. And the número 2, do f of x equals x cubed plus 3x squared minus 4x minus 12. Yep. Because the XY coordinate plane only contains real numbers. That's why visually there's nothing happening. But there's other math where you study greater complex numbers. It's called complex analysis. This upper division was.
Like the Z. Zero.
Has to do, yeah. There's that, exactly, yeah. No, we're gonna stay with this, but the last part of this is like kind of. Actually, figure out what the graph looks like. 100%. Yeah, because we technically have 31 minutes. Mhm. So it's not so much that this turn into this, it's more that all of this turn into this. So for example, let's say I distributed this whole term, this whole thing, and I distributed it here, and I distributed it here. Yeah, notice that the x minus 2 times the x squared is this part. 3x minus 2 and plus 1 is this part. So it's kind of like you're undoing that weird distribution. Exactly, this distribution comes from both directions. Yeah, that's one of the properties. So I can do it. Yeah, like technically I could have also written 3x minus 2 times x squared plus 1. Like I could have written this as well. And say I distribute this here, that's still x squared and 3 times 2. Here, that's still 1 and 3 times. Yeah, but you're not completely, like, you're not actually fully completing the distribution. So imagine it like this. Yeah. Then if I just remove the a from the left side, that'd be like that. So we're using this algebra trick to think of this a as being this whole thing. Exactly, just the way we did it today. Let me just remind you guys, this is called factor by grouping. If you have questions, work with your classmates. It's not a real zero, but it's a zero. It is, yeah, so 0 for the equation, but it's not a real zero. So, right, well, you guys will for the polynomial, find the y-intercept, find the x-intercept, and graph. And this is a 0 for it, in terms of graphing it, this doesn't tell you anything about the graph. Yeah, 0. And it's 0. Sorry. Good. That you're really You can do that. All right, guys, check your answers with your classmates. Do a quick little check. What's up?
Take an X out.
You can. But you can take it more than outside.
X negative 3 and then.
But so you want to take out the biggest x that you can. So you see in here, This one has 6 X's, but it doesn't have 4 X's. So what's actually the biggest X? Number of X's? Not 6, because this one doesn't have any.
So I can take out 3.
You can, but you can take out more than 3.
Yeah,
You could take out 4 more. Yeah, so you would take out X to the 4th and X to the 4th. So like this one right here. So here,
Yeah.
this says you can take out most 5 X's. This one says you can take out most 4 X's, but this one says you can take out most 3 X's.
Yeah.
But you need to take out the same number of X's for all terms.
Oh,
So therefore,
so, okay, so then this one would just become 16, and then this one will become X2.
Plus 4.
correct, correct, but you would take out, show me what it is that you would take out.
So we're taking out, I'm just doing,
Yeah.
And then the other one.
Good, yep, okay.
and then it'll be X2 plus.
Almost, so you took out, you're right, you're understanding that you take out negative
Yeah.
to the 4th, but you actually have to write.
Yeah, and you can't back.
Oh,
Yeah, so you have to show the reader, I'm taking out this many X's with the negative. And then I'm left with,
X2. Subtract 16.
not subtract, because you also took out the negative.
So add 16.
Correct. Yeah.
Oh.
Yep.
Like last week. Plus 1 was like the beginning of the class. We'll get a little-
I thought mine was zero.
Can't do this on my own. Is there more? I do it.
There's no factoring to do.
Yeah. Okay.
Yeah, so it's kind of like what we were here.
Yeah.
Now we just have to set each of these equal to 0.
Zero.
Yeah.
Okay.
I had to write some.
Oh, okay. Yeah, sick.
Yeah, I was planning to ask for your help, but I figured out what I.
Sweet, sweet.
No way.
When you set X squared as 16 as a whole.
Yeah, so real quick, class, I actually purposely stopped here, okay? So here, this one says X squared plus 16. This one says X squared minus 4, okay? This one, this term here has it's a special form. It's called the difference of squares term. No, this actually factors more.
Oh.
You can set it equal to 0 and you'll get the same answer. Okay, but I just want to review a little bit more factors. So this is called the difference of squares. And I think we talked about it.
Yeah.
So for the difference of squares, notice that this is of this form. It's like you're squaring the x, and here it's like you're squaring a 2.
It would be X times 2 or X.
Exactly. So this factors into x plus 2, x minus 2. Okay. If you set x squared minus 4 equal to 0, you will also get 2 solutions, plus or minus 2. That's because they're really factored into these two. Okay. So one of the 0 for this one is -2. The 0 for this one should be 2, and the 0 for this one, -3. Okay. Yeah,
If we can do it with X squared minus 4, do we need to factor further?
you don't, but it's gonna next week. It actually, you should.
It's something you can recognize.
It's something you can recognize, and it's something that's gonna become applicable next week. Yes. Here, the x is being squared, and here the 16 is a square. It's 4 squared, but it's not a difference. So in this case, these are what's called irreducible. It does not factor. Okay, so there's nothing to factor from there. So you just set it equal to 0. And we'll see why it didn't factor.
What happens with that one where it moves to like, because it's not squared, so what would happen when you multiply x times -2 and get like -2? Oh wait, no, this cancel out, never mind.
That's kind of the part of it,
Yeah.
yeah.
So for this one, is there a multiplicity? No.
This one has a multiplicity of 1, because there's only one true factor that it's a 0 of. So that's another reason. There's like some deeper theory happening here, but yeah, this was a 0 for this guy, right? But this wasn't fully factored. There's more. So this one is only a 0 for this x plus 2 factor, and there's only one of those here. So it has multiplicity 1.
But there are 3 multiplicities in total.
This has multiplicity 1, this has multiplicity 1. So in total, there's 3 multiplicities.
Yeah,
Yeah,
yeah, okay, so you have 3 multiplicities.
yes, yeah. Okay, this one, that's it, there's no more factoring. So in here, like you guys were saying, you're gonna set each of these equal to 0. And here you should get plus or minus 4i. Because the in-between step is that you got x squared minus 16. But that gives you the imaginary I. And then here, you set this one equal to 0. Before you fourth root, you need to get rid of that negative. So you divide by -1 on both sides. 0 divided by -1 is still 0. Now you undo the fourth power by fourth rooting. So I would get x, what's the number that multiplies with itself 4 times to give you 0? 0. Okay. Okay. I have to use the whole class time today. So no leaving early, unfortunately. All right. Okay. So now we're going to put a little bit of everything that we've done, and behavior, intercepts, all the algebra, to kind of figure out what the graph looks like now without a calculator, which is something you're going to do in calc. One of your tests is going to have you graph a function that's nasty like this without a calculator. But right now I'm just prepping you on how to do all that stuff. You know, because I care about you guys, you know, I want you to succeed in calc. That's the only reason I'm doing it. I mean, it's true. That is the reason I'm doing it. But okay.
There's no ulterior motive.
The paycheck is.
Oh, yeah, that's cool too. But that it's doing all this stuff is what I like about my jobs. Okay. So from the algebra we did here, where is it crossing the x-axis? Right here, right? Where is it crossing the y-axis? -12, the constant term. Where is it crossing the x-axis? 0 only. Where does it cross the y-axis? At 0 as well. So in this case, the x-intercept is also the y-intercept. Okay. All right. And behavior. And behavior. So we would look at your sheet and behavior.
It would be.
What's the degree?
Even.
Even?
So it'd be on the bottom.
So the graph has to look like that. So see, we're gonna put all those pieces together. We know the graph looks like this. We know it crosses at the at x equals 0 and y equals 0. But kind of now, where does the shape gonna end up looking like? That's the next part. Okay. So to do that, so putting everything together, we now need to figure out the shape of the polynomial that we're going to be dealing with. Polynomial. To do this, we use a sign chart to help us determine when y is positive or negative. All right, let me slow down, so super fast. Okay. We're gonna use the end behavior stuff, all the intercept stuff. And then let me show you how we're gonna do this sign chart. Okay. So let's use a sign chart to find where y is positive or negative. For the function, what do I have here for you guys? I already factored it for you. It's going to be 2x plus 1, x minus 2 squared. So, to begin this sign chart, you need to first figure out where the y values are 0. Another way of saying that is finding the function's zeros, because that is where the function equals 0. Okay? So what you're going to do first, is find the zeros of x. Which is why I had to do all this stuff. But I'm doing an easy one. It's already factored. Will the 2 help me find a 0? No, it has no x's. What makes this equal to 0? -1, and this 2. It's a 0 twice, that's fine, but just it's those are the zeros. Okay, now what you're going to do. So the second thing you're going to do is make a sign chart. Let me show you how you're going to design it. So imagine this is the x-axis. We know that at -1 and at +2, those x values make my function, the y value 0. Is that cool? So what you're going to do is you're going to split up your x-axis using the zeros. Like they're going to be like anchors. You're going to split it up, the x-axis. Like that. So what you're going to do is you're going to use test points with your sign chart. You're going to get an x value that's less than -1, and you're going to plug it into the function and see if the y value will be positive or negative. Okay, so it is a little bit of like tedious work. So pick a random x value that's less than -2. And we're going to plug it into the function, which is 2x plus 1, x minus 2 squared. All you care though is about the sign of the y value. You don't care about the actual y value. You just care about the sign, okay? So if you plug in -2, you're going to get 2 times. Is this going to give you a positive or a negative if you plug in -2? It's going to give you a negative. What is this going to be?
Positive.
It's going to be -2 minus 2, -4, but you're squaring it regardless. So it's positive. So if I multiply all this out, what kind of answer will I get?
Negative.
I'm going to get a negative. So that's what I really care, that I got a negative. Okay, pick, and now we're gonna pick an x value in between -1 and 2.
0.
Yeah, let's pick 0. So if we plug in 0 into the function, we're gonna get 2 times positive or negative. I'm gonna plug in 0 here. Positive, and then this will always be positive because you're squaring it. So whatever answer you get here, you have to square it. So it's gonna make it positive. So my overall y value will be positive. Okay. And now we pick an x value greater than 2. 3, sure. If I plug in 3 into my function, I'm gonna get 2 times a positive and a positive, so my overall y value will be positive. Questions on that process? The sign chart? Okay, so how are we gonna use this? Well, let's see. So if I'm gonna start trying to attempt to draw my polynomial graph. Where is it crossing the x-axis?
-1.
At -1 and at 2. But what my sign chart tells me is if I break it up into like these thirds here. Sorry, remember that means oops. All right, if I break up my XY plane like this, what does this part tell me here?
It's gonna be below the X.
It tells you that the y values on this side have to be negative. So is that the top or the bottom? The bottom. So the way the textbook does it, it says this is kind of like the restricted zone. Your graph cannot be here. It has to be on the bottom part because the y values are negative. So this area, this part of the grid is restricted. But between -1 and 2, the y values have to be positive. So are they going to be below the x-axis or above the x-axis? They have to be above the x-axis. So your graph cannot be down here. And then the same thing with this guy. The y values have to be positive, so your graph cannot be right there as well. Yeah, so now we know the graph has to live in this area, and it has to live in this area right here. Okay, yeah.
Does that mean when you're drawing it, it like stops at 2, 0 and just immediately goes right back up?
Stuff like that will happen. Yeah, exactly. So we know, okay. Does that picture kind of make sense?
Yeah.
So the x's are like restricted, do not enter zones. So the graph has to live here and it has to live up here. Okay. But now you're gonna put all of this stuff together. And behavior. What do the tails look like? Shit. See how it's in factored form? That won't, it won't be that helpful. We have to multiply it out to get the leading term. Okay, I'm sorry. I know. So notice that what we're gonna have to do. There's actually, I'll show you guys a shortcut. Okay. I have to multiply it out to get my leading term. So let's multiply this with itself twice. That'll be. Here I can distribute this 2 to help us. So that'll be 2x plus 2. And then here, when you FOIL this out, x squared minus 4x plus 4. And then if I FOIL that crap out, remember, you just want the leading term. You just want the leading term, the one with the highest exponent. So if you multiply this highest exponent in this factor with this highest exponent in that factor, it's going to be 2x to the third, and then I can keep FOILing, right? But do I need to?
No.
No, I don't care about the rest. I just care about the leading term. Okay? So if I kind of try to see a faster way of doing this, this will square my x, which it did. And then that x squared is going to multiply with this x, just x cubed, which then has to multiply with the 2. You give me 2x cubed. See that? Okay. What are the tails of this guy looking? The degree is odd, and leading coefficient is, so the tails have to look like this. So
By
that
degree, you mean the exponent?
by degree, I mean the exponent, correct, yeah, the biggest exponent. Which is why I didn't FOIL everything out, because these two will give me that biggest exponent, and that's all I really care about.
So even degree, if it's an odd degree, it's by the third.
And by the
And
third,
then,
this is the leading coefficient
okay.
is 2, which is a positive number. So that's what falls in here. Yeah. So that tells me that for my graph, as I approach x to negative infinity, what's the graph doing? Going down. And as it goes, the right tail is gonna go up. So I know the graph has to do something like that. Okay? What's the y-intercept? Well, let's plug in 0. It's okay. 2 times 0 plus 1, 0 minus 2 squared. That's going to be 2 times 1. Negative 2 to the power of 2. 4, which is 8. See, not too bad. Let's plug in 0. So then the graph is going to have to cross at 0, 8. So I know the graph has to cross here. What are the x-intercepts? We already got the zeros, right? Negative 1 and 2. So I know it's going to have to cross here and here. It has to touch those points. It has to. Okay. You guys do it. What do you think the general shape of the graph will look like now, knowing all these conditions? Get some time to think about it. Oh, it's 3:15, perfect.
Does everything else have to be exact?
It does not have to be exact, no, no.
Because my art skills cannot handle that.
So we know the graph, can the graph cross over here? No, because they can't have another x-intercept and it can't be above here, right? So it has to cross through here. So the graph has to cross, ooh, damn, through here to then go to the positive side. But it also has to touch here. So does the graph just keep going like that?
It has to touch the 8, doesn't it?
And it has to touch the 8s. And it
It
has to
goes a
touch the
little
8.
above the 8
Does it have
because
to-
negative 1 is farther or closer. Right?
Say it again?
It has to go above the 8 a little on the right side because negative 1 is closer to the 8. Or closer to the 0.
Possibly,
Yeah.
possibly, yeah.
Not
So-
front scale.
Things you guys are going to learn in a calculus class using derivatives is, does the graph go like this and maybe do some crazy shit like that? Sorry, crazy stuff like that? We don't know. Right now, we don't have the tools to know where these funky stuff happen. The derivatives are gonna help you with that.
So we have to go back down to the 2 and then up again.
Yeah,
Yeah.
sorry, Chris, say it again.
We don't know yet, but
All you know is that it has to cross here.
Yeah.
it has to cross it, or does the highest point have to be 8?
You don't know if the highest point has to be 8.
Okay.
Yeah, you don't know. We don't know. We don't have the tools for that. We just know that the general shape, it could go like this,
Mhm. And then.
but it can't go down, right?
So it has to
As long as
go,
we have it going back up and in.
Correct.
yeah,
Can it go back up like this?
yes.
No, polynomials do not have spike.
Oh, no, Mike, but sorry.
Remember?
Like you get a little loop.
And it has to have a little loop, some nice curvature like that. Okay? All right, guys, good job.
That's how they know we're.
Good job. You stuck through it. I like it.
It's kind of easy. Yeah, it's not that hard. When I saw it, I'm like, oh my God, it's so.
No, I don't even, if it was a 1+1, I wouldn't.
The first half was.
It got complicated.
But now we can wonder if there's actually
Yeah, yep. Good job, guys. It was one of those intense classes. Hella theory. Guys, I just want to say that normally it's okay if you're like a little lost right now, okay? This is where you go outside and you're like, you look at your notes again, and then you're like, okay, what the hell just happened? Start getting used, that sounds like fucked up, but start getting used to that feeling, because that's
Yeah.
kind of what's gonna end up happening. Because there's just so